Dear students, today we will study approximation algorithms. As we have discussed in some previous class, that how do we cope with hardness of problem, or how to deal with hard problems. I again repeating those things, that is what is the desired objectives or requirements from the solution of a problem. It should be, that is, our desired solution or our requirement is to find optimal solution. The second point, it should be we should be able to find it in polynomial time, and this solution should work for any instance. This is the three requirement of a solution. And as we know that if the problem is a hard problem, then we cannot achieve this simultaneously, these 3 points. In case of approximation algorithms, that is, we need to relax something from these 3 points. And in case of approximation algorithm, we relax the first requirement, that is, we relax about the optimal solution, and we want to find a near optimal solution, but the algorithm should run in polynomial time and it should work for any instance. So approximation algorithm is the algorithm which gives a near optimal solution, and it must be run in polynomial time and it should work for any instance. Why we study approximation algorithm? There are some points that is which motivate us to study approximation algorithms, because we need algorithms to get solutions to discrete optimization problems, and most of these are NP hard, and most of the real world problem and the problem we face often face, those problems are NP hard problems, but we need the solutions to, that is, make our life comfortable or our situation suitable. So we need some solutions, and since we know that if the problem is NP hard, then it is very unlikely that we will get an efficient algorithm. So we need to relax something, and here we are our target is to get some near optimal solution for hard problems, and that is why we study approximation algorithms. The second point is, because why we study? Because algorithm design often focuses on idealized models rather than real world applications. When we define some discrete optimization problems, and there are many some such situations, some constraints which make the problem difficult. And in fact, if we want to use it in real world application, then there are many constraints we need to meet in that, and that make the problem difficult. And when we study approximation algorithms, sometimes we assume some that is some model that is simplified model sometimes, and this gives us insight into the problem, and which helps us to face the challenge with the problem, because it provides a mathematically rigorous basis on which to study heuristics. What does it mean? When we that is use some heuristics or meta heuristics, we cannot guarantee the performance of the algorithm, performance of heuristics or meta heuristics. Okay, we have no mathematical that is guarantee for heuristics and meta heuristics. But if we study that problem for approximation case, and we study its mathematical foundation rigorously, then what will happen? We could identify that which of the instances are not good for heuristics. That is, heuristics cannot give good that is solution for which cases, or meta heuristics cannot give the good solution for which cases. We can identify those cases if we study approximation algorithms. And because it gives a metric for stating how hard various discrete optimization problems is. Here, it also actually that is in the last century, if we study how discrete optimization problems were handled by the researchers. In the early part of the century, researchers were concentrated with what kinds of problems could be solved at all by computers in finite time. For example, that is like halting problem. We have studied in some other course. And in the later part of the century, the researchers concerned with the efficiency of the solution. And particularly distinguishing between problems that can be solved in polynomial time and those are in NP hard, and that perhaps cannot be solved efficiently. So the field of approximation algorithm give us a means of distinguishing between various optimization problems in terms of how well they can be approximated. And finally, it is a fun because the area of approximation algorithm and its mathematical analysis is a very deep and beautiful mathematical exercise, and inherently it is interesting on its own right. So studying approximation algorithm and its analysis is really a fun who like to play with mathematics. So this is the reason why we want why we want to study approximation algorithms. Now, I just give a flavor of approximation algorithm by illustrating a very simple problem that we have already studied in some other courses. Just to bring a flavor of approximation algorithm, I am describing a very simple approximation algorithm of vertex cover problem. So in algorithm vertex cover approximation, we set the, here input is the graph and C is the set which contains the vertices, that is the vertex cover. So initially C is empty, and what we do, while G has still edges, we select an edge of G, say the end vertices of the edge is V and W, and we add vertices V and W to C. So we arbitrarily choose one edge from the graph and add that vertices V and W to C. We add in the vertex set cover, vertex cover set. And for each edge F incident to V or W, for each edge F incident to V or W, what we do, remove F from G. That means we are deleting all the edges incident to U and V, V and W. We are deleting all the edges which are incident to V or W and remove F from F end for. And this is our algorithm. And lastly, it is the end of the while loop. So this algorithm is very simple. Has everybody understood this algorithm? What is your response? Have you understand? Have you understood this?
Yes, sir.
Yes, sir.
So what we are doing, that is, we are given a graph, we choose any arbitrary edge, and let the two end vertices of the arbitrary edge we delete. Deleting, and we delete those vertices. Simply, if we simply say we delete those vertices, because we know deletion of a vertex is the deletion of that vertex and also edges incident to that vertex. So we delete those vertices, and then we check whether there is an edge or not. If there is an edge, then we choose an arbitrary edge and we delete the end vertices of that edge. So repeatedly, and when we choose an edge, we take the two end vertices of that edge into our vertex cover set, and finally we get a vertex cover. So this is our algorithm, a approximation algorithm for vertex cover problem. Now actually in our algorithm course we have studied this algorithm. In our algorithm course we have studied this algorithm. And can you anybody say what is the approximation ratio of this algorithm?
2.
Approximation algorithm হচ্ছে a ratio হচ্ছে 2. Approximation ratio is 2. So return C, this is our algorithm. So now the question is, how worst the solution? How worst the solution? For each edge, if you consider in this way, for each edge picked, we take two of its end vertices in C, whereas at least one of the end vertices of the edge must be in an optimal vertex cover. So C can contain at most 2 times the number of vertices in an optimal vertex cover. So the solution can be worst by a factor of at most 2. Is it clear?
Yes.
Is it clear to all?
Yes, sir.
Okay. Now we go okay, now we distinguish between feasible solution and optimal solution. Consider the vertex cover problem that we have just discussed, and this problem asks to find a vertex cover of minimum size among all vertex cover of a graph. So any vertex cover is a feasible solution of this problem. We are distinguishing between feasible solution and optimal solution. So our problem is to find a minimum vertex cover. So any vertex cover is a feasible solution of the problem. Thus an optimization problem is the problem of finding the best solution from all feasible solutions. So we can consider in this way when we will study some problems. That is, we first decide whether the solution we are obtaining is a feasible solution or not. So among the feasible solutions, the optimal one is our desired solution. So any vertex cover is a feasible solution of the problem, and thus an optimization problem is the problem of finding the best solution from all feasible solutions, and the best solution is the optimal solution. And hence an optimal solution of the vertex cover problem is the minimum solution of all feasible solutions of the vertex cover problem. So here just I want to distinguish between or make the clear about the concept feasible solution and optimal solution. Now we formally define performance parameters and approximability. First, we define alpha approximation algorithm. Alpha approximation algorithm. An alpha approximation algorithm for an optimization problem is a polynomial time algorithm. So approximation algorithm must be polynomial time algorithm, and that for all instances of the problem produces a feasible solution whose value is within a factor of alpha of the value of an optimal solution. So this is the definition of alpha approximation algorithm. So the algorithm we have studied from for a vertex cover problem is a 2 approximation algorithm. Is it clear? The algorithm we have studied for vertex cover problem is a two approximation algorithm. So is it clear to all?
Yes, sir.
Okay. Actually, this alpha, the value of alpha, there are many several conventions. Several two conventions like this. That is, sometimes it is less than one, and sometimes it is greater than one. It depends on the optimization problem, whether it is maximization problem or minimization problem. But as a convention in this course, we will consider that alpha is always greater than 1. Alpha is always greater than 1. Then the calculation of alpha for maximization problem and minimization problem will be different. But if we use the same formula for these two problems, then for some problem it will be less than alpha, less than 1, and some problem it will be greater than 1. But we are considering alpha is greater than or equal to 1. So here we need to calculate for maximization problem and minimization problem in a different way. For maximization problem, alpha is optimal solution divided by obtained solution. For maximization problem, the near optimal solution always less than the optimal solution, because we cannot reach the maximum. So this ratio will be greater than 1 or equal to 1, at most equal to 1. Is it clear? For maximization problem, alpha is optimal solution divided by obtained. This is optimal solution of the problem, and this solution is obtained by our algorithm. This solution is obtained by our algorithm. So alpha is optimal solution divided by obtained solution. And so since optimal solution is always greater than or larger than or equal to obtained solution, alpha will be greater than equal to 1. And for minimization problem, alpha is obtained solution divided by optimal solution. For minimization problem, this obtained solution, that is this solution, is obtained by our algorithm, and which is greater than or which is larger than or equal to optimal solution. So this alpha is greater than equal to 1. So is it clear to all this part?
Yes, sir.
Okay. Now we are defining a class of problem which is APX, approximable. We say it approximable class, APX class. The class APX, an abbreviation of approximable, is the set of NP optimization problem that allow polynomial time approximation algorithms with approximation ratio bounded by a constant. Sometimes we call it constant factor approximation algorithms. Constant factor approximation algorithms. So the class APX is the set of NP optimization problems that allow polynomial time approximation algorithms with approximation ratio bounded by a constant. So if we can devise approximation algorithm for a problem, or there exists an approximation algorithm for that problem whose approximation ratio is bounded by constant, then the problem is in class APX. In simple terms, problems in this class have efficient algorithms that can find answer within some fixed multiplicative factor of the optimal answer. So this is the definition of the class APX. The APX class, if a problem is in APX class, that is there exists an approximation algorithm for that problem with constant approximation ratio. So this class is APX. Now we define another terminology, that is polynomial time approximation scheme, PTAS. Polynomial time approximation scheme. It is called PTAS. What is it? If there is a polynomial time delta approximation algorithm with delta equal to 1 plus epsilon for any fixed value epsilon is greater than 0 to solve a problem, then the problem is said to have a polynomial time approximation scheme. If there is a polynomial time del approximation algorithm with del equal to 1 plus epsilon for any fixed value epsilon greater than 0 to solve a problem, then the problem is said to have a polynomial time approximation scheme, that is PITAS. The running time depends on input size and epsilon. The running time will depend on input size and epsilon. So the running time of this algorithm, PITAS algorithm, it depends on input size and this constant factor, that is this fixed value epsilon. Unless P equal to NP, there exist problems that are in APX but without a PITAS. There are some problems which is in APX but which does not have PITAS, unless that is P equal to NP. So the class of problems with a PITAS is strictly contained in APS. And then we define another term, that is fully polynomial time approximation scheme. Fully polynomial time approximation scheme, FPITAS. An algorithm that achieves an arbitrary good approximation ratio of 1 plus epsilon in a time that is polynomial in both n and 1 by epsilon is called a fully polynomial time approximation scheme. So then what is the difference between PITAS and FPITAS? Can anybody identify? What is the difference between PITAS and FPITAS? Do we have any response? No. Here, PITAS, it is mentioned here that the running time depends on input size and epsilon. But how it depends, it is not mentioned. Running time is input and epsilon. And here, it is mentioned that the running time is polynomial both in n and 1 by epsilon. So this is the difference. Polynomial in both of n and 1 by epsilon. Actually, if an approximation algorithm, its running time should be polynomial of input size, but we cannot guarantee about epsilon. It may be exponential on epsilon. But if it is fully PITAS, fully polynomial time approximation algorithm, approximation scheme, then the running time is is polynomial both in n and 1 by epsilon. This is the difference. Is it okay? Clear?
Yes, sir. Clear.
Okay. Then we proceed. So a problem is said to be APX hard if there is a PITAS reduction from every problem in APX to that problem. So we define the class APX like NP hard, the similar definition. So here APX hard, the problem is APX hard if there is a PITAS reduction from every problem in APX to that problem. And to be APX complete, if the problem is APX hard and also in APX. As a consequence, P not equal to NP implies PITAS not equal to APX. If P not equal to NP is assumed, no APX hard problem has a PITAS. So the relationships, here is a diagram, the relationship among these classes of problems. This all problems are NP hard problems. Among the NP hard problems, so this is the class APX. This is the class APX. Can you observe the movement of the mouse?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this is uh, the class APX. Inside APX, this is the class Petas, and this is the class Petas. So here the difference is, here the polynomial in n, but maybe approximation on maybe exponential of epsilon. But here both polynomial, running time is polynomial of input size and also polynomial of epsilon. So this is fully polynomial time approximation scheme, and this is polynomial time approximation scheme. And this is the APX problem, where this is the APX problem, that is where constant time approximation ratio algorithm exists. Here APX, and this is the class. This is APX hard part, and if a problem is both APX and APX complete, APX and APX hard, then it is APX complete. So this is the commonly believed relationship. We say it commonly believed relationship. We believe it. This is the commonly believed relationship among the class of this class of problems. Is it okay?
Yes, sir.
Okay. Now we will proceed. We will consider a problem for studying approximation algorithm, and we, as a working example, we are taking knapsack problem. This problem is well known to us. Again, I am describing the problem. We are given a set of n items where each item I has a price pi and a volume vi. All sizes and values are positive integers. We are considering everything is positive integers. The knapsack has capacity B, where B is also a positive integer. The goal is to find a subset of items S from I that maximizes the prices Pi of items in the knapsack, subject to the constraint that the total volume of these items is no more than the capacity. That is, if you sum up the volumes of these items, it should be less than equal to B. We assume that we consider only items that could actually fit in the knapsack. That is, no item has volume larger than B, so that Vi is less than equal to B for each I in I. So this is the knapsack problem. Everybody, we know this problem. Is it okay?
Yes, sir.
Okay. Now we consider a very simple version for studying, that is, we are playing with knapsack problem. So first we consider very simple version of this problem, where the price is the same as its volume. অর্থাৎ যেটা যত বড় সেটা তত দাম তত বেশি. Volume same as its volume. We first consider a simple version of the problem where the price is same as its volume. This is very simple version. Then the feasible solution for in any set that is sort set out O, such that Pi, if the feasible solution is the set O, then if we sum all the volumes of the set I, it should be less than equal to B. And also the prices will be also this sum. Prices will be at the solution. Problem is to pick a feasible solution which maximizes this one, because volume and price are the same. Have you understood this simple version of the problem?
Yes, sir.
So here actually volume and price, these are the same entity. we are considering this one as a very simple version of this knapsack problem. Now we devise a greedy algorithm. We devise a greedy algorithm for simple knapsack problem. Algorithm is like this: sort the items in non-increasing order of their volumes, and let V1, V2, Vn be the volumes of the items in non-increasing order. Then we choose first j items such that j is largest and sum of I equal to 1 to j is less than equal to b. Vi is less than equal to b folds. So this is the algorithm. This is very simple algorithm. Is it okay?
Yes, sir.
Okay. So that means here the original instances, and we have sorted this. So we will put, this is the knapsack, and we will put this largest one first, and then this one in this way, and until we can take until the largest item we can take. So this is the solution. So this is the greedy strategy. So this is our algorithm. Very simple algorithm. Now, this algorithm, we will claim that this algorithm is a true approximation algorithm. Why this one is a true approximation algorithm? We can easily show that the algorithm greedy knapsack, this name of this algorithm is greedy knapsack, is a true approximation algorithm as follows. If j equal to n, then all items have been chosen, and hence the solution is trivially optimal. If j equal to, if we can take all the items, then of course the solution is optimal. Is not it?
Yes, sir.
Okay. We thus assume that j is less than n. We thus assume that j is less than n. So if the first item v1 is greater than equal to b by 2, then clearly if the first item v1 is greater than b by 2, then that means if it is the case that we only can take the first item, then clearly alpha is 1 divided by b by 2 equal to 2.
Sir, can you please repeat it?
Okay. If we can take all the items, then the solution is optimal. Do you agree?
Yes, sir.
Okay. Now consider. So we consider the case that where we cannot take all the items. So we take less than n items. So in the first case, say if the volume of the first item is greater than equal to b by 2, that is greater than equal to half of the knapsack capacity, half of the knapsack capacity. If v1 is greater than equal to b by 2, that is greater than equal to half of the knapsack capacity, then clearly alpha is, this is just 1 means full b, that is actually this should be not 1, this should be b, that is optimal should be b, and divided by b by 2, and it should be 2. Okay.
Okay, sir.
Okay, so it should be 2.
So what is V1 here?
Here v1 is the items we have sorted. V1 is the items of the largest element, largest one. This is v1, this is v2, this is v3, this is v4, this is v5, this is v6, in this way. Have you understood?
Yes, sir.
Actually we
Sir.
have, okay, we have mentioned here, that is let
Sir, I have a problem.
okay, say please.
Sir, can you go to the picture?
Okay, yes.
Sir, as you can see, you cannot feed the fourth item, but if the picture is drawn to a scale, then you can feed the smallest item in the list.
Yes, we can fit the smallest items in the list, but our algorithm does not allow it. our approximation algorithm works in this way. That is, sort the items in non-increasing order of their volumes. This is our greedy algorithm. We are analyzing this algorithm. Okay, sort the items in non-increasing order of their volumes. Then say this is the, or in the non-increasing order, v1, v2, vn, with the volumes of the items in non-increasing order. Then we choose the first j items such that j is the largest, and this should be less than equal to b. Is it clear?
Yes, sir.
Algorithm is clear. So we are following this algorithm here, and we are analyzing the analyzing this algorithm. Okay, so if you change the algorithm, then you can pick that is this smallest one here. But the algorithm we are following, it does not allow this one. Is it okay? Clear? Or you have any question?
Clear, sir.
Okay, so we are analyzing this algorithm, remember. So if v1 is greater than equal to b by 2, that means the worst case, in the worst case, we have taken only one item, and all other items, the second item also, its volume is greater than equal to b by 2. So we have taken only one items, and in that case also clearly alpha is less than equal to 2. If v1 is less than b by 2, then every item has volumes less than b by 2. In this case, items 1 to j has been packed, and item j plus 1 cannot be packed due to lack of space. Since every item has volume less than b by 2, the item 1 to j has taken space larger than b by 2. Thus, the approximation ratio alpha is less than equal to 2. Is it clear, the last part? Every item has volume less than b by 2. So we are packing the one after one another in the in the sorted order, and eventually sometimes we cannot take someone. So, but the spaces, the remaining spaces must be less than b by 2. That is, we have occupied the spaces is greater than equal to b by 2. Is it clear? Thus, the alpha is less than equal to 2.
Yes, sir.
Here, actually, optimal solution will be at most b. Optimal solution will be at most b. I have mentioned here, just wrote here 1. Okay, so if we check, calculate it, it will be 2, and it will be 2. So I think it is clear to all.
Yes, sir.
Okay, now we consider tightness of algorithm greedy knapsack. Tightness of algorithm greedy knapsack. We now check the tightness of algorithm greedy knapsack. For any n is greater than 3, any arbitrary large even b, consider an input instance of length n having volumes b by 2 plus 1, b by 2, b by 2, b by 2. So this is our instance. We are considering for an instance. This is the input instance. This is the input instance. Okay, and algorithm greedy knapsack chooses the first item, which results in a situation where no more items may be chosen. That means if this is the instance, the greedy knapsack will choose this one, and then this cannot be fitted. This cannot be fitted. No other item cannot be fitted in the knapsack. So any optimal solution may choose only 2 items, except okay. So we can, but if we consider about the optimal solutions, then optimal algorithm, any other optimal algorithm, it will skip the first item, and it will take, say, any two of the items. So the optimal solution will be b, but our solution, greedy knapsack solution, will be b by 2 plus 1. So this one, thus alpha is 2 divided by this ratio, which tends to 2 with increasing b. If the b size of the b is increased, then if you consider this equation, if size of the B is increased, then it will be tends to 2 with increasing B, and hence alpha is tight for algorithm greedy knapsack. So it mentioned that the algorithm greedy knapsack is tight approximation algorithm in a sense that there is an instance for which this algorithm gives tight approximation ratio. Is it okay? So this is our last slide of today's class. So if you have any question on this lecture, you may ask me, and in our next classes, so it is a constant time approximation ratio. The problem is in APX. So our goal will be find some better approximation algorithm, say PITAS or FPITAS. So in the next classes, we will study those. So if you have any question on today's class, then you can ask me.